Okay, let's get started then. So this is for triple scientists only, C3 revision, and we're going to cover all of the topics very briefly that come up. Now, the first thing that I want to say is actually for C3, there's no real guessing of the topics. There's fewer topics and pretty much everything will come up. If we look back from 2015 and 2014, you've got periodic table comes up both times, water comes up, your molecules, so your carboxylic acid, your esters, and your alcohols. Energy comes up quite a lot, so it could be Q equals mc theta. It could be energy in terms of hydrogen or energy bonds. The Haber process, that was molecules again down there, and titrations or titration calculations and identification of ions. So this was just me looking through the questions from 2015 and 2014, and there's no real guessing. Fewer topics and pretty much everything will come up, and you need to therefore be prepared for everything. So let's go through then. Don't miss out the periodic table, okay? People think that it's easy and forget key points. First of all, early periodic table, you had Newlands and Mendeleev. Now, Mendeleev was the guy that left gaps. They both tried to order them in, he tried to order them in groups with similar properties. With Newlands, he was putting every eighth element in these similar properties. But Newlands fell down. He had things like iron in with oxygen. He had metals and non-metals together because he didn't leave gaps for undiscovered elements. Both of them were ordered in terms of atomic mass. Okay, so all of their elements were increasing in terms of atomic mass, which is different to what we have now. Newlands, he called that the law of octaves, because every eighth element was similar, so he tried to group every eighth element together. And Mendeleev, you need to be able to recognise as the one with gaps. Now, it might not look like this one in exam. They might have a bizarre one with gaps in to put you off, but just remember that this would be Mendeleev's one. So now we get to the early periodic table, and there's a few trends that we need to remember, and feel free to write all over these in your data sheet. So first of all, now, rather than going up in atomic mass, we go up in atomic number. So each element has a different atomic number, and that's what we go up in. So actually, if you look along the periodic table, some of the atomic masses go up in a little bit of a weird order, okay? They don't go up each time. So for example, here we go 262, 266, 264. Okay, it goes a little bit up and down on the atomic mass, but the atomic number is always increasing because that's what we put them in now. Again, we group them with similar properties. Group number tells you how many shells there are in the outer shell. We need to remember about this one, the alkali metals. Over here, group 7, the halogens, and noble gases over here. Now, these two we need to know in a bit more detail. The alkali metals increase in reactivity. Now, this is a key bit on the high paper, and things that in higher tend to always come up. So here, the trends in reactivity within the groups in the periodic table can be explained because the higher the energy level of the outer electrons, the more easily electrons are lost, or the less easily electrons are gained. So this is a key bit that you might want to pause and have a look at in a minute for the higher paper. And essentially all that means is over here where you've got a lithium atom, the positive part of that atom is pretty close to the outer shell electron. So there's a big electrostatic force keeping that electron there. But all the way down here at francium, the positive part would be really far away from the outer shell electron. So the higher the energy level of the electrons, the more easily electrons are lost. So rather than being close to this positive nucleus, actually these are really far away. There's lots of electrons shielding them, so we call this electron shielding. And this electron is easily lost. So francium is really reactive. The opposite way round is the reactivity for the halogens. So the halogens increase in reactivity as you go from bottom up. Okay, and if you draw a simple one out, it will help you explain why. Because at the top, the halogens, remember, are gaining electron. So if you have the positive nucleus and an outer shell close by, it means when it's got those 7 in the outer shell and it needs to gain 1, it's really close, okay? Because it's here, this distance is really close. And if the electrons are really close, then they easily gain an electron. But if it's far down the bottom, it's astatine down here, you'd have the nucleus in the middle and your electron shell's really far away. So actually, because they're far away, they are less easily gained. The higher the energy shell, the less easily gained they are, because it's not a big enough force to drag that electron into that outer shell. Okay, so just bear that in mind for the high tiers, it always comes up. Also, you need to think about them in terms of melting points and boiling points. So as you go down the alkaline metals, they have lower boiling points and melting points, whereas the opposite is true for the halogens. Okay, so everything's always in opposite pretty much. They have lower boiling points up here as you go down this way, and lower melting points. So draw these, feel free to draw these on your periodic table as you go into the exam. Secondly, we need to think about some reactions. So first of all, halogens, normal displacement reactions like you'd see with other things. For example, chlorine can react with potassium iodide, which is balanced there. Because chlorine is more reactive than iodine, because it's higher up, it will displace that iodine and you'd end up with iodine and potassium chloride. Okay, so simple displacement reactions before, but just remember that this group halogens can do those as well. With the alkali metals, you need to remember the experiment where they react with water that you would have seen in class in a big trough of water. First of all, you'll notice that they have a low density. They float on the water. And when they float on the water, they react with the water and give off a gas. That gas that's given off is hydrogen. So for example, if you had sodium, adding to water, you would make sodium hydroxide plus hydrogen. And of course, because they are alkali metals, this is an alkali given off, sodium hydroxide. Okay, so just bear that in mind. A couple of reactions associated with the alkali metals and the halogens that we need to know about. Energy then always comes up. Bear in mind that this might be in terms of calorimetry or working out the calories of food. So this here, you could be looking at burning a food or a fuel and heating up water to see what the temperature rise was. And just like in physics, when you have the equation E equals m times c times theta, this is exactly the same here. Energy released by the fuel is mass times 4.2, which is the specific heat capacity of water, times the energy change. So if we want all the energy from this fuel to go to the water, we need to make sure this is insulated. So they might ask you to improve the experiment by perhaps adding insulation, adding a lid, and making sure that all the heat from here is going into the beaker. Maybe having a insulating material on the bottom, for example. And then we just use the numbers in the question to work out the energy transferred, or perhaps we arrange it to work out the mass or temperature change or something like that. So really, really common question. They might ask you to perhaps set this up, maybe in a method question, or they could ask you to work out a calculation. Now, you may well in physics have seen the specific heat capacity of water as 4,200. That would be in joules per kilogram degrees C, but because we've got it in grams, our mass in grams, this is the specific heat capacity in joules per grams degrees C. So if you get it as 4.2, just make sure that your mass is given in grams as well. So, as well associated with energy, you will get these energy diagrams for endothermic and exothermic reactions. You just need to be able to read them and put them into a sentence. So with these ones, just say to yourself, the energy of the reactants is lower than the energy of the products. So the products must have gained energy. Energy must have been taken in. So it must be an endothermic reaction. On the other one, the energy of the reactants is higher than the energy of the products. So energy must have been given out. So that is an exothermic reaction. And here, the difference in energy is this delta H. Delta meaning the difference and H meaning the energy. Okay, so the difference in energy, and in this term heat energy, given out. So they'll say, how do you know this graph is endothermic? And the answer they want is the idea that the energy in the reactants is lower than the energy of the products. They might ask you to work out, draw a line on to show the activation energy. So a line from the reactants up to the top to show the activation energy. Remember for C2, the energy needed for the reaction to happen, similarly over here. And they also might want you to draw on there where the effect of a catalyst. So remembering a catalyst provides an alternative pathway with a lower activation energy. Also in energy, they talk about bond energies. This is a specific thing on the higher paper, so it's pretty much guaranteed to come up. And this is the important thing we need to remember. In an endothermic reaction, the energy needed to break the bonds is greater than the energy released from forming new bonds. Whereas in an exothermic reaction, the energy released from forming new bonds is greater than the energy needed to break the existing bonds. And the key thing that you need to remember for this question is that energy is needed to break bonds. So it's taken in when you want bonds broken. And it is released, which is quite weird, it's released when bonds are made. So it's given out when bonds are made. Key point to remember, and maybe write this in the white space around your question. And they will give you a table in relation to the bonds in a particular example and the bond energies that they have. Now, what they tend to do to make it a little bit easier is they will give you the actual shapes of the bonds in the molecules that you are using. So here, for example, they give you N triple N, okay, is N2. And they give you the HH and the NH. So over here, N2, we need to balance it first of all. That's the thing that people miss out. We need to balance it. You'll recognise this as the formula for the Haber process. So N2 plus 3H2 goes into 2NH3. So when we're working out the bond energies, well, we've got N2 here, and we need nothing more. That is the molecule N2. So we need 944. And we need to add that to 3 lots of hydrogen to hydrogen. So 3 lots of 436. And that will give us the bond energies on this side. So using your calculator, you do 944 added to 3 times 436, and you'll end up with 2252 on this side. On the other side, you've got 2 lots of these molecules, 2 lots of ammonia. So you've got ammonia has 3 NH bonds in. So already you're talking about 3 times 386. But then you need 2 of those. So you need 2 lots of 3 times of 386. So over here, in total, you would have 2316. And therefore, if you have a look here, this is the energy needed to break the bonds, and this is the energy released when bonds are made. So you've got 2252 on this side, 2316 on this side, kilojoules per mole. So therefore, if you take this away from that one, you will end up with 2252, take away 2316, which will give you minus 64 kilojoules per mole. And this minus from before tells us that this is an exothermic reaction. But also, if you tell yourself in words, it will tell you, because less energy is needed to break the bonds, and more energy is released when bonds are made. Okay, so the energy is being released overall. Overall, if you look at this, more energy is released when the bonds are made than is taken in when the bonds are broken. So this is in relation to this statement here about exothermic reactions. So you might be asked to do a calculation like this, and it will say, how do you know that it's an exothermic reaction? And this will be your answer. More energy is released when bonds are made, as opposed to is taken in when bonds are broken. So really common question to come up. And just remember to balance your equation first of all. Have a look at what bonds you've got going on, Do your calculations a couple of times because sometimes they're quite close, and make sure that you have these keywords in your answer. So just a question on, do they give you the specific heat capacity formula on the past question that we did? Let's just go back to that just a sec. Yes, they do. You're really lucky. They tend to give you in the question this formula here, Q equals M times C times delta T, and they tend to give you, or they will give you, the 4.2 as well for the water. So they give you that equation and you don't have to work it out, because obviously for physics you don't get, sorry, for chemistry you don't get equation sheets like you do in physics. So moving on then to the biggie, the Haber process. And the reason that I've put all this text on the screen is not so that you have to read it all, but we'll go through it, but it's just to show you how much higher tier content is associated with this Haber process. So expect it to come up. Let's have a look at the general equation and discuss why all of this stuff comes up. So first of all, like the equation we had before, nitrogen from the air, hydrogen from natural gas is used to make ammonia. But the problem is it's a reversible reaction, and we can just balance it like so. Trouble is it's a reversible reaction, and you have 1 mole of nitrogen for every 3 moles of hydrogen. There's no number there, so we've got this ratio of 1 to 3, making ammonia. But also, at the same time, ammonia is breaking down and making these 2 products here. So you've got 2 things going on. Now, at a point, they will reach what we call an equilibrium. And this is the first thing that I want to cover. They will sometimes ask you, what does it mean by an equilibrium? So you will need to remember that an equilibrium is reached when the reactions occur at exactly the same rate in each direction. So that is your definition of an equilibrium, when the reactions occur at the same rate in each direction. Okay, so in the forward direction, which we call this one, and the backwards direction, or the reverse direction, when they reach equilibrium, the reaction will occur at the same rate. And it will look like the reaction stopped. It will look like nothing's happening, but stuff is happening. It just means that ammonia is being made and these products are being made at the same rate. Now, if we want to shift that equilibrium, if we want to move it to favour this direction and making more ammonia, or if we want to move it into this direction to making less ammonia, then we can change the conditions. So we can change the pressure, or we could change the temperature. Now, of course, we want to, in this Haber process, make ammonia, because this is a useful fertiliser. This is the whole point of this process. Now, we could then change these conditions of pressure and temperature to make sure we get a bigger yield, a bigger amount of ammonia out. Okay? And what happens is we do this in a closed system. This Haber process happens in a closed system. So you'll get the gases going in at the top, and it will have an iron catalyst throughout. And there'll be a tap at the bottom that you can extract the ammonia from. But whilst the reaction's happening, then there is no reactants going in or out. Okay, the system is closed. No reactants or products can move in or out. It's a closed system. And we can adjust the conditions in there like so. So this gets a little bit complicated. So I'll just start off with temperature first of all. Just clear the page and start off with temperature. Now, we said we've got nitrogen and hydrogen coming together to form ammonia. And with this reversible reaction, in one direction, it is exothermic. We worked that out on the previous question. And just like in C2, if it's exothermic in one direction, it must be endothermic in the other direction, because in a reversible reaction, if it gives out heat one way, it must take in heat the other way. Now, with temperature, if we increase the temperature, have a think, which reaction are we going to favour? Are we going to favour something that gives out heat, or are we going to favour something that needs heat and takes in heat to break the bonds? We're going to favour this one, aren't we? We're going to favour the endothermic reaction. So if you increase the temperature, then more ammonia is going to break down into its products. So that is bad. What we would really want in an ideal world is ideally we would want a low temperature, because that would favour the forward reaction. Okay, so ideally we want a low temperature. But there's a problem with that, and that's in relation to our collision theory and our rates of reaction that we looked at in C2. If it's a really low temperature, unfortunately, even though we get a bigger yield of ammonia, the reaction is really slow. So a low temperature would be great, but the reaction is too slow. So rather than having it at a really low temperature, our compromise is at 450 degrees C. That is the temperature that you need to remember for the Haber process, 450 degrees C. Now let me put that into words to try and explain. Well, let's say you wanted a 50% yield of ammonia, and that was a high yield, and you did your experiment at 20 degrees C. So you did it at a really low temperature and you were getting a really nice yield. But can you imagine if it took 3 hours to get to that yield? It would take a really long time. So what would be a compromise then is, rather than that, going for a slightly lower yield, say 25%, and doing it at the higher temperature of 450 degrees, but it taking a lot less time. So maybe just 20 minutes this time, for example. So yes, a lower temperature would be better to get more ammonia out, okay, because a higher temperature favours this part of the reaction, turning it back. So we don't want a higher temperature, we want a low temperature, but if the low temperature would make the reaction too slow, because if you had a really low temperature, it might take ages to get that yield out. Because if you remember from C2, if you increase the temperature, you increase the rate of reaction. So really difficult conceptually to understand, but that's how you need to know that this is a compromise temperature. It's not the ideal to get the yield, but it's the best to get the most yield in the quickest time. Secondly, pressure then. With pressure, this goes down to the fact that we've balanced our equation. So on the left-hand side of the equation, you've got 1 molecule of nitrogen and 3 molecules of hydrogen. And they are going to make 2 molecules of ammonia. Now, if you increase the pressure, so if you were to squeeze all of this together, then this would favour the side where there are more molecules. So if you increase the pressure, you increase the ammonia yield that you get, the amount of ammonia. Yield just means amount, okay? So you increase the amount of ammonia that you get. Could you imagine? Because if you push these 2 particles together, there's still quite a lot of space for them. But if you squash these particles together, because there's 4 molecules, they are going to start reacting and making more ammonia. So these points are all given in these higher level bits, okay? So the amounts of the reacting substance at equilibrium depend on the conditions, fine, temperature and pressure. If the temperature is raised, the yield from the endothermic reaction increases and the yield from the exothermic decreases. If the temperature is lowered, the yield from the endothermic decreases and the exothermic decreases, so they're just the opposite of each other. And in gaseous reactions, an increase in pressure will favour the reaction that produces the least number of molecules. So in this case, the reaction will favour this way because we're producing a lower number of molecules. So when you're talking about pressure and why it happens, you're talking about the fact that here you've got a larger number of molecules than on this side. So it will favour producing the yield for the molecules, for the side of the reaction where there are fewer molecules. And then this bit comes together. These factors, together with the reaction rates, are important when determining optimum conditions. So you need to remember that the optimum atmospheric conditions are 200 atmospheres. Now, even though down here we've said that an increase in pressure would increase ammonia yields, but our problem is the systems that we build cannot withstand massively high pressure. It's too expensive and it's just too unsafe to build systems that have a massively high pressure. So this is our compromise. So just in summary, our compromised compromised positions are 200 atmospheres of pressure for the Haber process and 450 degrees C. This one, because of high pressure, means more ammonia, but we can't build these expensive high pressure systems. And this one, because even though a low temperature would mean higher ammonia, it's not fast enough, okay? The reaction at a low temperature is not fast enough. So this is our compromise. So the reason why I've gone in so much detail about this is that this part comes up in the spec. Describe and evaluate the effects of changing the conditions of temperature and pressure on a given reaction. So I just want to highlight to you that it might not come up in terms of the Haber process. They may well throw a curveball and start talking about a different reaction. They might give you the detail about endothermic, exothermic, and talk about a different reaction. If not, because of this big statement, maybe there's enough to talk about for a 6 marker. Okay, so that was the Haber process. Just a couple more things to go through, and then that is it for the evening. Again, I am going on late because of technical difficulties, so feel free to stop now, and then you can just recap this bit in the morning. So titration calculations. The main thing that you need to remember with titration is the method and the setup. So they could ask you a method question. Okay, how do you set it up? What would you do to accurately measure how much acid, for example, is needed to neutralize a certain amount of alkali, like sodium hydroxide, for example. But they also want you to work out, and again, this is a high bit of the content, work out the titration calculations. So let me give you an example to work through. So this example is if you have 15 centimeters cubed of 1.2 molar hydrochloric acid, how much 0.8 molar sodium hydroxide would you need to neutralize it? Okay, and the first thing you need to do here is make sure the equation's down. Now in the exam, they'll probably give you the equation. The first bit might be to balance it. But when you think about what's going on, we're reacting with hydrochloric acid with sodium hydroxide, an acid and an alkali from C2 make a salt, so sodium chloride plus water. So in this case, we've got our hydrochloric acid and sodium hydroxide. We need to make sure it's balanced. So let's just check. 2 H's there, 2 there, 1 oxygen, 1 Cl and 1 Cl. So we're all balanced and fine. Now the next thing we've done after we've balanced it is we draw out our table of acid against alkali. So I had a question on doing one of these, so hopefully you'll be able to catch up with this one. Acid and alkali. And then the final thing is to think about what equation we're using, which is N over C times V. They do not give you this equation on the test. You need to remember this. If you want to remember it in a picture format, like some of you have done already, you're thinking about the number of moles divided by car times by a van. Really weird way to remember it, but some of you seem to remember it that way. Okay, moles over car times van. The number of moles equals concentration times by volume. So now we write down in our table all the information that we've got. We've got NCV, NCV. So for our acid, what have they given us? They've given us a volume and a concentration. Okay, actually in your exam, they'll probably write that out as moles per decimeters cubed. And again here, moles per decimeters cubed. Now, because they've given us that clue that this is in decimeters cubed, this is the tricky bit. For our volume, we need to put that into decimeters cubed. So let's put our information in the table. Volume of acid, we've got 15, but we need to divide that by 1,000 to get it into our decimeters cubed. We've got a concentration of 1.2, and we don't have information about number of moles. For the alkali, we've got a concentration of 0.8, and we don't have information about volume or number of moles. Now, volume is what we've been asked to work out. So then you look, what can I actually do in this equation? What's the next thing I can do? Well, the only thing you can do is work out this, because you've got the values to work that out. So you do N equals C times V. So the number of moles is 1.2 multiplied by 15 divided by 1,000. And that will give you the number of moles of acid, which would be 0.018. Now, you still can't work out anything over here because you need to work out the number of moles. And remember, you've done that by the balanced equation. So here, there is 1 mole of hydrochloric acid for every 1 mole of sodium hydroxide. So the ratio is 1 to 1. So quite simply, we just need to put that number over here. Now, if that was 1 to 2, you might need to double this one. Or if it was 2 to 1, you'd have to halve it, okay? But in this case, we'll just put it straight across. And now you can see, now we've got that bit of information, we can work out the volume by doing 0.018 divided by 0.8 to give us 0.0225 decimeters cubed in this case, because we've divided it by 1,000. If you want to convert it back to centimeters cubed, you would times by 1,000. So have a look careful what the units are for the question. Okay, so top tips then for titration calculation: write the balanced equation, write out the table like this, and write out your equation. And once you do that, you just work out what information you need to work out, or the only bit that you can work out, and then refer back to your balanced equation. So really common question to come up in the higher paper for C3. Couple more topics to go. We're going to talk about molecules quickly, and the molecules that we need to know about for C3 are alcohols, carboxylic acids, and esters. Again, as I said, feel free to leave and watch this tomorrow morning if you want to. I don't expect you to stay on and listen this late. So alcohols then, they all have the names which start with the things that you would have looked at before in C1. Monkeys eat peanut butter. The starters of the words meth, eth, prop, and bute. Okay, so alcohols such as methanol, ethanol, propanol, butanol, etc. And with alcohols, they have a specific functional group, which is OH. That means there's an OH molecule on the end of these alcohols. And if you are asked to draw methanol, my advice to you would be to draw the methane that you remember, and then remember that instead of H, it's got to have OH on the end, okay? And that would be your methanol. And you do the same if you wanted to do, for example, propanol, where you'd have 3 C's with your H's on the end for propanol. And then you can just write the functional group on the end, which is OH. And you need to remember that that is the functional group. And all of these are part of the same series called a homologous series, which means they are only differ by a single kind of unit here. So they all a very similar structure, all got the same functional group, but they only differ by a single parameter, a single thing. So those are the alcohols: methanol, ethanol, propanol, butanol. You might be asked to draw any of these top 3 ones or write their formula. Now, their formula seems to show off their functional group, actually. So, for example, methanol would have the OH on the end, and then it would be your CH3. Okay, so CH3OH. So you're taking that bit there, and then you're writing that bit there. For this one, you might see it as CH3, CH2, CH2, OH. And they might write it in a really long way like that. All that's doing is it's saying, right, that bit's there, that bit's there, that bit's there, and then we've got the OH on the end. So they kind of have that bit to show off and show that it's an alcohol. So all you need to do when naming them is just make sure you're counting the carbons. So you can see OH is an alcohol, and then 1, 2, 3 means that it's got 3 carbons, so it must be propanol. Now, there's a few reactions with alcohols that you need to know. You need to know that they are a useful fuel and a useful solvent. So in relation to fuel, you'll need to remember that they can combust, okay? So like ethanol in cars, they will react with oxygen, so an alcohol plus oxygen. just like other fuels, will make carbon dioxide plus water. And you also need to know that they react with sodium, so alcohol plus sodium, and they will make something called sodium ethoxide. They'd be really mean if they asked you to name that, but they will expect you to know that hydrogen gas is given off. So then we can get from an alcohol to a carboxylic acid by oxidizing it or adding oxygen. And you can either do this two ways. You can either use a chemical oxidizing agent to add the oxygen, or you can rely on microbial action. Okay, so just like when you open a bottle of wine and you leave that open to the air, you'll end up with a vinegary taste because inside you would have made a carboxylic acid. Now these react just like other acids, so they will react with an alkali to make salt plus water, for example, and they react a similar way with all other acids. Now for the carboxylic acids, basically they've got a really complicated name, but actually they're quite simple. And the ones that you really need to remember are methanoic acid, ethanoic acid, and maybe also propanoic acid as well. They won't really talk about butanoic acid very much. So ethanoic, ethanoic, and propanoic acid are the ones that we need to remember. Now, when drawing those, you need to remember the functional group is COOH. Okay, that's a functional group for carboxylic acids. So if you start with that, if you start with the C double bond OOH, you can work your way back. So for methanoic acid, for example, one carbon. Remember, each carbon can have 4 bonds. So 1, 2, 3. It's only got one left. So that's our extra H. And that would be our methanoic acid. For ethanoic acid, again, start with the functional group on the end. So start with COOH and work your way back. We need one more carbon and we need to add the hydrogens on the end. Okay, so start with the functional group, work your way back, and you can't go wrong. And again, these will have these funny symbols. So you show off the COOH on the end, and you'll end up with CH3. So just remember to count the carbons in there. 2 carbons, so it must be ethanoic acid. And then we can go to esters. Okay, now to get to esters, we are reacting an alcohol with a carboxylic acid. To react these two things together, and you make an ester plus water. Okay, so I'll just write it down here. Alcohol plus carboxylic acid makes an ester plus water. And the only ester that you need to know about and worry about actually is ethyl ethanoate. So you need to recognize that that's an ester, and you need to recognize that that's made from ethanol reacting with ethanoic acid. So don't worry about naming things like butanol, propanoate, or anything like that. That's the only one that you'll be worried about. And you don't have to, well, I very much hope you don't have to draw it. You just need to remember that the functional group in the middle looks a bit like that, in the middle of a long, more complicated molecule that I'm not going to completely draw. So you're looking out for this functional group, which we call COO. Now, the main thing with esters is knowing that they are fruity smelling. They are volatile, which means they turn into a gas easily, which makes them also flammable. And they also are used in things like perfumes and flavourings and things like that. Now, the final thing, so we're talking about alcohols, carboxylic acids and esters. The final thing is this point here. And I'm going to stress this really importantly because this is a higher tier piece of content which pretty much comes up every year. And because it's higher tier, expect to see it. So it says, I'm going to clear all this stuff off now. It says, carboxylic acids do not ionize completely when dissolved in water, so they are weak acids. Aqueous solutions of weak acids have a higher pH value than aqueous solutions of strong acids of the same concentration. So to give you an example, that suggests that we have hydrochloric acid, our standard acid, and a carboxylic acid, for example, one we haven't written before, so propanoic acid, C2H5COOH, okay? Or you might see that as CH3CH2COOH. And all it's saying is if you had 0.1 molar hydrochloric acid and 0.1 molar carboxylic acid, when they dissolve in water, this one completely ionizes. So you will have lots of hydrogen ions in there, making it a strong acid. Compared to, strong in comparison to, this carboxylic acid, which will have fewer ions in there, which are going to make it an acid, because it doesn't completely ionize when it's dissolved. So it doesn't release lots of these hydrogen ions when it dissolves. So they are a weak acid. So if we were to measure the pH of these when they're dissolved, this, for example, might be pH 5 for argument's sake, and this, even though it's the same concentration, could be pH 3. So that's one thing you need to bear in mind. Why are carboxylic acids weaker acids? Because they don't completely ionize. So they might say, well, how come we've got 0.1 molar of this and 0.1 molar of that, but this is a weaker acid? Don't forget the pH scale goes from 1 to 7 for acids and up to 14 for alkalis, okay? Or sometimes you'll see this as 0. So this part is the acid, so if it's closer to 7, closer to neutral, is going to be a weaker acid. So really common thing that comes up in the higher tier paper is this extra bit here. And you need to remember that carboxylic acids don't completely ionize, so they end up being weak acids. 2 things to go then, and then we're all done. Let's talk about water, and then let's talk about identifying ions. So water, we can either have hard water, or we can have soft water. Now the ions that make hard water are magnesium ions and calcium ions. But they're all 2 different types of water. There is one that is permanent, or so-called permanent, and there is one that is temporary. Now for higher tier, you'll need to remember this, so expect it to come up. The temporary water contains something called hydrogen carbonate ions. So for example, in there, you might have calcium hydrogen carbonate. And those ions in there would make the water temporary. And what that means is when it's boiled, it will turn soft or turn into soft water, okay? Because temporary hard water contains these ions that decompose on heating. So when you boil your water in a kettle, if it's temporary, you will produce calcium carbonate or magnesium carbonate, which will form a precipitate, and that will be the scale in your kettle, and that will reduce the efficiency of your kettle. But if you want your water soft, it will make it soft. On the other hand, then you have that permanent hard water, or so-called permanent. We'll talk about so-called why in a minute, and they tend to be your calcium sulfates and your magnesium sulfates and things like that. But you can have a mixture of both in your water. This is important. You could have some water that has some properties of permanent water and some properties of temporary water because of the ions that are in it. And actually, hence why I put this permanent in brackets, both of these can be softened. Okay, you can soften both of these types of water either by adding something called washing soda or sodium carbonate, or by putting it through an ion exchange resin. So with an ion exchange resin, essentially what you've got is a column of beads, a column of resin, and on that resin you have sodium ions, Na plus or Na, sodium ions, and they will essentially just exchange with the magnesium ions that are going through. So the magnesium ions or the calcium ions are in the hard water. They will exchange with the sodium ions that are on the resin. So essentially that's all you need to know, is that the hard ions in the water will swap with the sodium ions. This is a continuous process. And all you'll end up with is more sodium in the water. So that might be a little bit of a downside, but at least you get rid of those hard ions, those magnesium and the calcium in there. The other one then was adding sodium carbonate. Okay, that's more of a batch process. We had advantages and disadvantages of this one year. Okay, there's a batch process. Obviously, you don't have to. After a while, you'd have to exchange this resin, but it tends to work for quite a long time. That's a downside. You'd have to exchange it and replace it. But you can add washing soda and use sodium carbonate to soften your water. And what will happen is the carbonate ions, if we draw it in a different colour, these carbonate ions in sodium carbonate will react with your hard water, so your calcium ions, and give you calcium carbonate again. So your precipitate, this solid substance, which will then be filtered out of your kettle, or cause a load of scale and stuff build up in your kettle, and obviously reduce your efficiency. Okay, so hard water or soft water. Hard water contains these ions. Temporary hard water is the one that contains hydrogen carbonate, but you can soften both. Now the key thing is it might have a mixture, and they might talk about a table of results. If you've boiled the water, don't forget that will mean and it goes soft, that will mean it's temporary. Remember, if I just clear this, that hard water needs more soap. So it's more cost for cleaning companies to produce a lather or to produce bubbles. So you can use a titration to test whether your water is hard or soft. So you could have, for example, your water in here, and you want to know, is it hard or is it soft? In here you'd have your soap solution, and you would record how much soap is needed to produce a constant lather of bubbles. So you might put a little bit in, swirl it, a little bit more in, swirl it until you've got a permanent lather of bubbles on top of your water. Okay, so this can test whether it's hard water or soft water. You can also have a look, well, if it boils and that gets rid of it, these hydrogen carbonate ions that produce a precipitate, that will be temporary hard water in there. So your water might have these ions in, and also calcium ions and magnesium ions as well. A couple more things with water. Obviously, if you store it in a reservoir, you first need to filter it. You then would need to perhaps add chlorine to the water, perhaps, or also in relation to chlorine would kill the bacteria or disinfect it. Also, you might want to add fluoride, and that is to make your teeth better. Supposed to be a smile. It's not really getting there, but that's supposed to make your teeth better. But obviously, there's some downsides because everyone has fluorine in the water in some areas. Okay, you don't get a choice. Some people will link that to cancer. There's no evidence for it, but obviously that's a controversial thing, adding fluoride to water because you've got no choice about it. Right, final thing, and then I'll let you people go, is the identifying ions, okay? And feel free to come back to this. I'm just going to give you a couple of tips to remember it. Now, what I recommend you do in your C3 Triple Science exam is to try and write down on the white paper this pathway to help you remember anywhere on your page. So, first of all, why do we do this? So let me just give you an example. If you have a particular white powder, you might want to know, well, what is it? I've just found it. Is it an illegal drug? Is it a certain substance? Could it be harmful to me? How can I find out what it is? So for this compound, it'll be a mixture of a metal ion and a non-metal ion. So maybe magnesium chloride. It could be copper chloride or copper iodide, for example. Could be pretty much any substance. And what you need to do is work out two bits. First of all, you need to work out, well, what is this part on this side? And what is this part on this side? And this bit is a metal ion, so this is testing for the positive ion. And this bit is the negative ion, testing for the negative part of it. So you could do several things. First of all, you could do the flame tests. And you will need to remember the colours for the flame test. So I remember it as Britain's got really clever students overthinking the learning of pretty coloured lights. That just helps me remember that barium is green, calcium is red, sodium is orange, potassium is lilac, see, you always forget, and lithium is crimson. Okay, that's just my way to remember it. I know loads of you got different rhymes to help remember it, but I remember it as Britain's got really clever students overthinking the learning of pretty coloured lights. And some people think barium green for other reasons, okay, like green bogies or whatever it is that you've got to remember them. Write them down, just the letters in the column to help you remember the flame test. That's one thing you could do. You could put a dab of this powder into the flame and see what colour it went. If that didn't work, to find out the positive ion, you could do this. You could add sodium hydroxide. And if it went green, it would be iron 2. And we call that iron 2 because the transition metals can either be ions which are 2+ or ions which are 3+. So it could be Fe2+ or it could be Fe3+. Or, so for example, that dirty green precipitate that would be made would be iron 2+. Fe3+ would be an orange or dirty brown precipitate. And then we've got a light blue precipitate, which would be copper. So if we added sodium hydroxide, this is the bit that you need to remember. This is the bit you're adding, sodium hydroxide, and it can make these three. Remember, these are all transition metals, all colourful compounds. Now, the other thing that they can make, which makes it complicated, is a white precipitate. So the solid that comes out could be white. And this poses a problem because it means, well, it could be calcium, could be magnesium, it could be aluminium. Now, the next step we need to do is add excess sodium hydroxide. So to the white precipitate, we'd add more than we need, okay? Add excess. And one of these will disappear. The precipitate will disappear. And how you remember that, or how I remember it, is aluminium. If we say it like the Americans, where they call it aluminum, that sounds a little bit like a spell. That sounds like a little bit like something's going to disappear if we say aluminum. Something out of Harry Potter, maybe. So if we add excess sodium hydroxide, the aluminium or the aluminum will disappear. So in this case, we'll finish off our flow diagram. Add excess sodium hydroxide. If the white precipitate disappears, it means you had aluminium in that compound. If it stays, it'll either be calcium or magnesium. And in this case, you would then do a flame test. And if it was red, you'd know you've had calcium. And if there was no colour change, you would know you've had magnesium. So back to our compounds. If we say we went all the way through this and we ended up with a white precipitate that went red, we know we've got calcium as the first part of our substance. We don't know what it is though. It could be calcium carbonate, could be calcium bromide, could be calcium iodide, could be calcium sulfate. This next step we need to do is to work out the negative part. So the final thing then is working out the negative part. And there are 3 tests that you can do. First of all, there's the halide. So remember on the periodic table, these are group 7. And they are called the halogens. And I remember this, a couple of tips to help you remember. Halo, I remember it as a silver halo. Okay, so a silver halo, which is why we're adding silver nitrate. And the nitrate sticks with the nitric acid. So nitrate, nitric acid, and you end up with the test for a halide. So this is saying, is my negative ion in that white powder anything to do with group 7? And in group 7, you've got the chloride, the bromide, and the iodide that we need to talk about. So if you add dilute nitric acid to that white powder that you've got, and silver nitrate, are you going to end up with a white precipitate, a green precipitate, or a yellow precipitate? And if you do, you can see whether it's a chloride, a bromide, or an iodide. And to remember the colours, one's yellow, one's cream, one's white, one's cream, one yellow. If you think about this in terms of group 7 on the periodic table, it goes darker as you go down the group. So you start off with white with chlorine, which is near the top, and then you end up with cream, and then yellow. So they go darker as you go down the group. The second test, finally, is sulfates. To test whether that negative ion is a sulfate, if you add dilute hydrochloric acid and barium chloride. So again, the hydrochloric acid and the chloride stay together. And if you add that to your powder and you find that there's a white precipitate, you know that there's a sulfate. And the reason being is because of this barium in here. If you react the barium chloride with your white substance, you'll end up making something called barium sulfate, and that will mean a white solid. Okay, and the final one is carbonate. So the final one is what you probably would have done several times in school before, and that is carbonates, adding dilute acid, and what you do is you turn lime water cloudy, sorry. So carbon dioxide is produced when you add dilute acid to a carbonate, and that will turn lime water cloudy. So the hint I will give you, well, this one is maybe quite easy to remember because you've done that a lot in class. This one, if you remember halos, silver halos and silver nitrate, nitric acid, darker colours down the periodic table. This one for me is the trickiest one to remember. Adding sulfate to test for sulfate, sorry, is this barium chloride and hydrochloric acid. So that is the final test, and then you could find out whether your substance, for example, was, we said it was going to be calcium, so it could be calcium chloride maybe, it could be calcium bromide, it might have been calcium carbonate, and this final test would have worked out this part of the compound. So I've just had one quick question that says, isn't sodium yellow? Yeah, you might see the flame test for sodium. You might see it as yellow or orange. Okay, they shouldn't discriminate in the exam whether you choose yellow or orange because they're so familiar in colour. So if you've learnt it as yellow, keep that as yellow in your head. If you've learnt it as orange, that will be fine too. And it says, if there's a 6 marker about water, can we write it just like calcium, or would we have to put calcium 2+? If you're talking about the ions in the water, you can talk about that simply as terms of in hard water there are calcium and magnesium ions, but just be aware in your exam, if it wasn't a 6 marker, or in the 6 marker you could put it in brackets like that. Okay, if you're wanting to write in full sentences, but just bear in mind that you might see it as these ions as well. Okay, thank you very much for watching. Again, I apologise for the final time about the technical difficulties that I had earlier. Feel free to ask me any further questions you've got on Frog, and I'll get back to you on there. If not, pop up and see us tomorrow and we'll give you a hand. And once again, thank you for Mr. Crowley for letting me use his Hangout sessions, as mine did not work, or YouTube did not allow them. Okay, so get lots of rest tonight, sleep well, and be ready for your exam in the morning. Make sure that you have a good lunch and that you're all ready and prepared for your exam. You've already put all the hard work in, so just read up on any last little bits that you need, or ask any last questions, and you should feel ready for tomorrow. So thank you very much for listening, and have a good evening.